equal to dimension of length and dimension of breadth. So the dimension of area is L into L. So finally we get the dimension of the area, L square. So finally we should write like this, L square. Enough, right? This one is enough, like this, right? We don't need to write like this, okay? This is the L squared. So here M naught T naught. So M naught, value of the M naught is 1. And also value of the T naught also 1. In mathematics, each number have a 0 powers, that value is 1. So here finally we can write L squared, right? So only we can write L squared. That is enough. So area of the dimensions of the area is L squared. Other one is volume. Volume equal to area into depth or length or something, right? So volume equal to length and breadth and the height. So these three are lengths. So here also dimension of the volume equal to dimension of length, dimension of breadth, dimension of height. So we are using square bracket. Dimension of volume equal to dimension of length into dimension of breadth and dimension of height. So here these three are lengths, L into L. So three capital L's. So here we can get the L cube. So dimension of the volume equal to L cube. If I ask in the questions what is the dimension of the volume, we can write only L cube. It is enough. Okay. We don't write L cube and the M naught and T naught. These are the values are 1. So 1 into L cube equal to 1 L cube. So here L cube. So the L cube is enough. Right. Other example. Density. Density is equal to mass over volume. So dimension of density equal to, we can write like this, putting the square bracket. Dimension of the density equal to dimension of the mass over dimension of the volume. So here mass, dimension of the mass is capital M, right? Dimension of the mass equal to capital M. Over the volume, dimension of the volume equal to L cube. So we can get dimension of density is ML cube, ML minus Q. So this one is positive. So in the upside, M into L minus Q. So density, dimension of the density is ML minus Q. So you should write like this. ml minus q. This is enough. Other one is velocity. The dimension of the velocity equal to dimension of displacement over time. So here displacement, dimension of the displacement is capital L, and dimension of the time is capital T. So we can write L T minus 1. Here L over T, here the power of T is positive 1. So this T1 go to upside, so L into this power is going to minus, so LT minus 1. So velocity, the dimension of the velocity is equal to LT minus 1. So LT minus 1. Another one, acceleration. Dimension of the acceleration equal to change in velocity, dimension of the change in velocity over dimension of time. So here change in velocity, so the dimension of the velocity is LT minus 1. Here time T. So here LT minus 1 over T. So this T going to upside, so this positive power going to negative, so L into T minus 2. So the dimension of the acceleration is equal to LT minus 2. Another one is pressure. The dimension of the pressure equal to force over area. So dimension of the force. So how to find the dimension of the force? We know the Newton's law, F equal to ma. In your O-level studies, you know it. F equal to ma, force equal to mass into acceleration. So the dimension of the force is equal to dimension of the mass and the dimension of the acceleration. So here dimension of the mass is capital M, and the dimension of the acceleration is LT minus 2. So here we can write dimension of the force MLT minus 2. So here force over area. So dimension of the pressure equal to force over area. So we already write the dimension of the force is MLT minus 2. So over area. So dimension of the area is L squared. So finally we can get dimension of the pressure is MLT minus 1 T ML minus 1, sorry, ML minus 1. This L square going to upside, so this one is L to the power minus 2, here L to the power 1. So finally we can get L to the power minus 1 and T minus 2. right? So the dimension of the pressure is equal to ml minus 1 t minus 2. If you have any doubts, please ask me. Okay.
Okay.
So here is a force that we already write it. Okay. Another one is momentum. The momentum is equal to mass into velocity. So dimension of the momentum equal to dimension of the mass and the dimension of the velocity. So we know the dimension of the mass is capital M and the velocity equal to LT minus 1. Finally, we can get the dimension of the momentum equal to MLT minus 1. Another example of dimension, impulse of force. So dimension of the impulse of force equal to force into time. So here the dimension of the impulse of force equal to force into time. The dimension of the force equal to ml minus 1 t minus 2. And the time is t minus 2, the multiply by capital T. So here we can get the force sorry ml t minus 2. So here ml, this one is t to the power minus 2, this one is t to the power 1. So finally mlt minus 1. So this one, impulse of force equal to mlt minus 1. This dimension equal to another quantity. That one is momentum. This one mlt minus 1. So here, impulse of force equal to change of momentum. We will study about this. Impulse of force equal to change of momentum, right? In mechanics, we will study about what is the meaning of momentum, what is the meaning of impulse force, right? So you don't worry about this. We will study about detailing in mechanics. So here, impulse of force equal to change of momentum. Another example, kinetic energy. So here, kinetic energy, dimension of the kinetic energy equal to here, this one half is the amount, right? This is the constant. So half is the value, right? So value don't have the then dimensions. So here numbers don't have the dimensions. So here mass and the velocity square only have the dimensions. So the dimensions of the kinetic energy equal to mass into velocity square. So the dimensions of the velocity is LT minus 1, all things square. So the dimension of the kinetic energy equal to ml square T minus 2. So here you should uh, know about this. Okay, constant don't have the dimensions. The numbers of constants don't have the dimensions. So here these are the numbers only. Okay, so here mass and velocity square have a dimensions. Another one is electric charge. Electric charge equal to electric current into time. So this one is new dimension. Okay, electric charge and electric current. Here the equation of the electric charge equal to dimension of the electric charge equal to electric current into time. This equation also we will study in the electricity. Okay, so here the electric current, the dimension of the electric current is capital I, and also dimension of the time is capital T. So dimension of the electric charge is IT, capital I into T. Do you have any doubts in this dimensions?
No, sir.
Okay. In some physical quantities have a special names of units. Okay. Here force, the unit of the force is Newton. So the Newton is capital N. Right? This unit of the Newton is capital N, because Newton is the name of one of the scientists. So here we are using scientist first name letter as a unit. Uh, we should write in capital letters. So the force is, unit of the force is capital N, Newton. And other one is kinetic energy, energy work done, unit of the energy and the unit of the work done also. We are writing the units in joule. So here joule also one of the scientists. So here we are writing the unit capital J, joule. So these are the special units of the physical quantities: Newton, joule, and watts, coulomb. So here coulomb also one of the scientists, capital C. And watts, volt, ampere, right? These are the special names. Ampere, capital A. This one is unit of the current, and volt, this is the unit of the electric potential, and watt, this is the power of the electric. And also another one is Pascal. So capital PA. Pascal also one of the scientists. So these are the examples of the special names of the units. These are the first letters of the scientist names: ampere, volt, watt, Pascal, Newton, Coulomb, Tesla. Right. Right. Another right. Next one is applications of the dimensional analysis. Right. We are using dimensions for the many words. So these are the applications of the dimensional analysis. So first one is we are using check the correctness of physical equation. So we are going to use the dimensions for the to check the correctness of the physical equation. Another one, to find dimensions of the new physical quantity. Third one, to derive the form of physical equation. The last one, to derive the relations between the different units of different systems of physical quantities. So these are the applications of the dimensional analysis. So firstly, we can see the to check the correctness of the physical equation. So firstly, example 1, to check the correctness of physical equation. Here v equal to u plus at is the one of the equation, where u is the initial velocity, v is the final velocity, a is the acceleration, and t is the time. So in this equation, we are checking the correctness of this physical quantities. So here v equal to u plus at. So in this equation, normally we know that same physical quantities must add or subtract. Okay, here we want to add or subtract any physical quantities, that physical quantities should be same physical quantities. Okay, we can add mass and another mass, right? M1 plus M2. So these are the same physical quantities, mass and mass, right? So we can add 1 kilogram and plus 2 kilogram is equal to 3 kilogram, right? And also we can add T1 plus T2. These are the times. But we can't add mass and time because these are two different physical quantities. We can't add this one because M1 is mass, T1 is time. These are the two different physical quantities, right? Like also we can subtract M1 minus M2. So here this V equal to U plus AT. So this multiplication of the A into T equal to physical quantity of this u. So that is mean u plus at. Okay, so this a and t multiply by multiply a and t is equal to physical quantity of u, and also these are equal to physical quantity of p. Okay, because this is the equation v equal to u plus at. So here a and t is multiplying, right? A and t are multiplying, that multiply physical quantity adding with u, that is equal to v. So here we are right like this. So here this equation, this part, right side of your right hand side, this one is left hand side. Okay, this one is right hand side, right hand side, RHS. This one is left hand side. So here first you write left hand side. The dimension of the left hand side is equal to velocity, final velocity. The dimension of the final velocity is LT minus 1. So write like this, LT minus 1. And right hand side, RHS equal to U plus AT. Here dimension of the right hand side equal to U plus AT. Here U and AT is equal. So multiply A and T multiplying and the U equal to AT. So here the dimension of U is LT minus 1. Here A's dimension of the acceleration is LT minus 2 multiply by T. So we can get here T minus 2, here T1 minus 2 plus 1. So finally LT minus 1. So V is the dimension of the final velocity is LT minus 1. Here initial velocity LT minus 1, and multiplication of A and T is equal to LT minus 1. So here right hand side, dimensions of the right hand side physical quantities all are equal. U dimension of U is LT minus 1, and dimensions of A and T multiplying A and T is finally we get the LT minus 1. So here right hand side quantities have same dimensions LT minus 1, and also left hand side also have a LT minus 1. So right hand side equal to left hand side, hence by principle of homogeneity, right, the given equation is dimensionally correct. You should write like this. Okay, you first you give the dimensions of physical quantities, then write left hand side, another step right hand side. So put the dimensions of that physical quantities, then check the right hand side and left hand side. Those are equal, so LHS equal to RHS. So finally you write like this. So this equation is dimensionally correct. This is the common step for the all. Check the correctness of the physical equation. So another example of correctness of the physical equation, equation of v square equal to u square plus 2as. Here v equal to final velocity, u equal to initial velocity, a acceleration, s is a displacement. So here we can first write v square, dimension of v squared equal to dimensions of u squared plus dimensions of as, because 2 is a number, so numbers don't have the dimensions. So here left hand side, dimensions of left hand side equal to here v square. So v is the final velocity, so lt minus 1 all things squared. We can get the dimensions of v square is l square t minus 2. In another step, right hand side. So here right hand side u square plus as. So here u also velocity, so l square t minus 2 plus dimension of acceleration is lt minus 2, dimensions of displacement is l. So here l into l multiply by l square, right? So here l square t minus 2 plus l square t minus 2. So right hand side, dimensions of the right hand side equal to dimensions of left hand side. So here LHS equal to RHS. Hence the principle of homogeneity is the given equation is dimensionally correct. Another applications of the dimensions to find the dimensions of the new physical quantities. So how to find the dimensions of the new physical quantities? The examples of this first one, find the dimensions of the universal gravitation constant. This one is gravitational field. We will study in field, gravitational field. We studying in this equation F equal to gmm over r square. Here m1 and m2 are masses, r square is the length, so F is equal to force. So here we are going to find the dimensions of gravitational constant. So here F and R cross multiplication F and R square over M and M1 and M2 dimensions of M1 and M2. So we know the dimension of force MLT minus 2 and here R is the length, so L squared over this one too. These two are masses, so M squared. So we can simplify this one M, here M squared, so this M squared going to upside M to the power minus 2, here M to the power 1, so m minus 1 L cube T minus 2. So we find the dimensions of gravitation constant G is m minus 1 L cube T minus 2. So you write like this. Another one is find the dimensions of the coefficient of viscosity. So here F is the force, A is the area, so dV over dx is the velocity gradient, right? Gradient of velocity, right? Gradient velocity. So here this one is we will study in mechanical properties. This one unit 9 or something. So here we are going to find the dimension of this one, viscosity, coefficient of viscosity, neta. So neta equal to F into dx over V into dV. So here the dimensions of the force is mlt minus 2. The x is length. So dV over dx means velocity gradient. So velocity, dimensions of velocity is lt minus 1. This one is dx mean small length. dV and dx, those are small values. That is the mean of dV over dx, the change of velocity of a change of distance. Those are small values. So lt minus 1 over L. So here L is, here A is area. So we are putting in this equation, dimensions of neta is dimension of force mlt minus 2 and dx is L, A is area, and also dV, velocity lt minus 1. So finally we can simplify this one. Here m, here L cube, this one is L square, so L minus 1. Here T minus 2, here T minus 1. So this T minus 1 going to upside T plus 1. So here T minus 1. So ML minus 1, T minus 1. Then dimension of neta is ML minus 1, T minus 1. Another constant is electrical permittivity. So here F is force and Q1 and Q2 are charges and R is a length. So distance between these charges. This one is a electric field. Okay. So electric field force equal to 1 over 4 pi epsilon. So here 4 pi is the value. This one is constant. So epsilon naught equal to dimensions of epsilon naught equal to, we can write q squared, because this q1 and q2 are charges, over dimensions of F into R squared. So dimensions of charges, we know I into T. So I squared T squared over force. Dimensions of force is MLT minus 2 and R is the length, so L squared. So finally we can simplify this one. M minus 1 L minus cube I squared T4. So this is the dimensions of epsilon naught. Third application of the dimensions to derive the form of physical equation. Okay. The example of this applications of this to derive the form of physical equation. Here, the period capital T of the simple pendulum is assumed to depend on length L of the pendulum, acceleration due to gravity G, mass m of the bob of the pendulum. If the constant of proportionality is 2 pi, then find the equation for the time period of the simple pendulum. So here they ask the relations between time and mass, length, and gravity. So first we can write T proportional to L to the power x and G to the power y and M to the power z. So in this case, first we should like this T proportional to L to the power x, G to the power y, M to the power z. We are going to find the values of x, y, z. So here they ask, find the equation for the time period of the simple pendulum. So they ask time period of this simple pendulum, relations between L, G, and M. That is, we write T proportional to L to the power X, G to the power Y, and M to the power Z. Then these are the proportional relations. So we should write equation. So here we are multiply by constant K. K is a constant. This proportional relations convert to like this equation: T equal to K into L to the power X, G to the power Y, and M to the power Z. So here K is a constant. Okay, here K is a constant. They given this one. If the constant of proportionality is 2 pi, so here K is a 2 pi. We can use this value at the end of this calculations. Okay, so here the equation is T equal to K into L to the power X, G to the power Y, and M to the power Z. Next step is, we know the dimension analysis. So dimensions of time equal to, the K is a constant, so K don't have the dimensions. So length have a dimension, gravitational acceleration have a dimension, and mass also have a dimension. So here L to the power X, and G to the power Y, and M to the power Z. So here L is a length, L to the power X. G is the acceleration, so LT minus 2 or to the power Y, so Ly T to the power minus 2y. And also M is mass, capital M into Z. So here this capital T is a period of the oscillation, so the oscillation time. So dimensions of the oscillation time is capital T. So right hand side we have a length, time, and mass, but in left hand side we have only time. So here we can write M to the power 0 and L to the power 0. That is, the value of M to the power 0 is 1 and L to the power 0 is 1. So here M naught and L naught. So these are the values of 1. So not affected this equation. So here first we equate the power of the mass. Left hand side is 0, right hand side M to the power Z. So Z, the value of the Z is 0. Then we equating the power of length. Here left hand side 0, right hand side here L to the power X into L to the power Y. So equal base multiplying the powers are powers will add. So L to the power X plus Y. This is the basic mathematics. So here X plus Y equal to 0. So here X equal to minus 5. Last one, I'm going to equate the power of t. Here power of t is 1, left hand side. So right hand side minus 2y. The power of t is minus 2y. So here y equal to minus 2. Y equal to minus half, sorry, minus half. Then here x equal to minus y. So x equal to minus y. So minus into minus plus. So x equal to half. Here now we can put in the powers. T equal to k into L to the power 1. So L to the power half, g to the power minus half, m to the power 0. So here m to the power 0 is, the value of m to the power 0 is 1. So finally here balance t equal to k into L to the power half and g to the power minus half. So we can write like this: t equal to k into L to the power half. So this one, g to the power half, L over g. So this value of the power of the half is root value. So t is equal to k into root of L over g. So this is the equation of the period of oscillations. T equal to k into root of L over g. Here they give the value of k is 2 pi. So t equal to 2 pi root of L over g. This is the equation of oscillation of the time period, right? Time period of the oscillations in the length and the gravitational acceleration. So t equal to 2 pi root of L over g. So here another example. The centrifugal force F acting on the body is assumed to depend on the mass of the body, its linear velocity v, and the radius of circular path r. Show that. So wave of they ask the equation of centrifugal force in using the mass, velocity, and the radius of the circular path. So first we can write F proportional to m to the power x, v to the power y, and f to the power, sorry, f proportional to m to the power x, f proportional to v to the power y, and f proportional to r to the power z. Then we are right combine f proportional to m to the power x, v to the power y, and r to the power z. Then we are going to convert the directly proportional to this relations like equation. So F equal to K, we are multiplying by constant K, mx, m to the power x, v to the power y, and r to the power z. Then we are putting the dimensions of force equal to, equating the dimensions m to the power x, dimensions of mass, dimensions of velocity, dimensions of radius. So F is the force. We know the dimensions of the force mlt minus 2. The m is the mass, so capital M to the power x. Here velocity is lt minus 1. So the lt minus 1, all thing y, so ly t minus y. Here r is the radius, so L to the power z. Then we are going to equating the power of m. Here left hand side power of the m is 1. Here x, so x equal to 1. Then equating the power of L. Here left hand equal to 1, right hand here L into L to the power y into L to the power z. So base are equal, so powers are adding, so x y plus z. Then equating the power of time minus 2 here minus y. So y equal to 2. Then putting the value in this equation, z equal to minus 1. We simplify this equation, that is minus 1. So here putting the value f equal to k to the power k into m to the power 1 and v to the power square v to the power 2 and also r to the power minus. So here f equal to kmv square over r. So in this equation, k is the value of the k is 1. This value is derived from the many practicals. Okay, so here f equal to mv square over r. So here k is the value is 1 is the value of k. So f equal to mv square over r. The equation of force and the relations between the mass and velocity and radius. This is the circular motion, centrifugal force. F equal to mv square over r. Another usage of the dimension is finding the dimensions of unknown physical quantities. In this equation, S equal to A plus BT plus CT squared. Here A, B, C, write the quantities A, B, C. So here these are equations. In these equations, dimensions of S equal to dimensions of A equal to, here B and T multiply by that quantity is equal to A quantity or S quantity. And also this one was physical quantity. Okay, these are the same physical quantities. A equal to B into T and also C T square, because this is the equation we already see this Same physical quantities are adding or subtract. Other one is we can't add and subtract. Here A adding with BT and also adding with CT square. So those are this B and T multiply B and C. Finally, we get the equal physical quantity of A. Then we can write S is the displacement. So dimensions of displacement is L. So here we can equate S and A. So dimensions of A is L. Another one is equate S and BT. Here S is the length displacement. So we should calculate the dimension of B here multiplied by T. So T is the capital T. So dimensions of B is LT minus 1. So that is the dimensions of velocity LT minus 1. Then CT square equal to S. So dimensions of S equal to dimensions of CT square. So here dimensions of displacement is L and T to the power 2. So here T to the power minus 2. So dimensions of C is LT minus 2. This is the acceleration, dimensions of acceleration. So here A is the length displacement and B is the velocity and C is the acceleration. And also see this equation P plus A over V squared into V minus V equal to R into T. So P is the pressure and A is the here what is the dimensional formula of A over B? So V is the volume. Okay, first we find the B and A. In this equation, this totals multiplied by V minus B. So here V is subtract from B. So here dimensions of V and B are equal because same physical quantities must subtract. So dimensions of B is LQ because B is the volume. So dimensions of B is LQ. Here also dimensions of P equal to dimensions of A over V squared. Because P adding with A over V squared. So P is the P and A over V squared are same physical quantities. So pressure equal to force over area. Force MLT minus 2. So over area L squared. So ML minus 1 T minus 2. and also dimensions of A. Here volume square. So volume square mean L to the power 3, all things square mean L to the power 6. So here they ask dimensional formula of A over B. A over B. See, or A over B. So here this L to the power 6 cross multiply by L to the power minus 1. So ML 5T minus 2 and over L cube. So finally we can simplify M L squared T minus 2. The dimensions of A over B is ML squared T minus 2. So last one, last equation is F equal to A sine CT plus B cos dx. So here F, dimensions of F equal to dimensions of A. In this equation, sine CT. So we know that the plane angle and the solid angle have only units. They don't have a dimensions. So here sine CT and cos dx, they don't have a dimensions, because other sine, the sine, example of sine 30, we have the sine 30, unit of the sine 30 is half. This is the value, this is the constant. So we don't have sine and cos, we don't have the dimensions of sine and cos. Okay, so we have only have dimensions of A and B. So F is the force, so A and B have same. They ask A over B and C over D. Okay, they ask A over B and C over D. So here sine CT don't have a dimensions. That is mean the value of 1, because they don't have a dimensions. That mean M naught, L naught, T naught. So these are the values of M naught, L naught, T naught is 1. So here C into T, multiplication of C into T equal to 1. Dimensions of C into T multiplications, C equal to 1. Then dimensions of C is T minus 1. This T divided 1 over T. So here T minus 1. And also here D to the power D into X. D into X, multiplication of D into X also equal to 1. The dimensionless meaning is they don't have dimensions. That is mean m to the power 0, l to the power 0, t to the power 0. So that is the value of this one is t. So here the dimensions of d is l minus 1. X is the displacement. So in here l minus 1. So C over D is equal to LT minus 1. So C over D, dimensions of C over D equal to LT minus 1, and also A over B equal to here 1, because sine C, sine C, this one sine is the value, right? Sine, angle of the sine is value. So constant, they don't have the dimension. So we can write 1. So A into 1, B into 1. So F dimensions of A equal to dimensions of A and B. So here A and B are same dimension. So A over B is a dimensionless quantities. Okay, I finished today class. I will send these notes in your chat box. You do it this questions again and ask me any questions in this question in this examples. If you have any doubts, please ask me. Okay, today we finish this, and
Okay.
okay, wait a minute, I will send the notes